Welcome back. Today we're going to be looking at how to determine if a reaction is endothermic or exothermic. This is some reference table work, so having that handy will be helpful to you. So this do now question, explain in terms of particles why an increase in temperature increases the rate of a reaction. So go ahead, this video will pause to let you answer this question. All right, so questions that have this in terms of phrase, you need to mention what is going on with the particles that causes an increase in temperature to result in an increased reaction rate. So you could say, as temperature increases, particles have greater average kinetic energy, so more frequent collisions occur. Anything with reaction rate, you want to talk about what the particles are doing and how that causes a change in collisions. This is a really quick lesson. It's a nice kind of ease your way in, plus it's a lot of just reference table reading. So the first thing here is talking about what is the heat of a reaction. So just looking at this phrase, everything has some sort of heat or energy content to it. The heat of a reaction is the total amount of heat given off or absorbed over the course of the reaction. So the way that that is calculated is that you're finding the difference between the energy of products and the energy of the reactants. And we symbolize, anytime we talk about change, we use this delta H, change in heat. So all processes have some sort of delta H value. Some of this is a review for you. We've already talked about what it means to be endothermic and exothermic. Now we're going to put like numerical values with this. If we have an endothermic reaction, enter, energy is absorbed overall. So there's going to be some energy absorbed, some energy released, but overall you have an absorption of energy. So here, if I have an example where my reactants have 5 kilojoules of energy and my products have 10, when I do my delta H calculation of products minus reactants, I get 5 kilojoules gained overall. All the time, if you have if you have an endothermic reaction, the delta H is always going to be positive. And then exothermic is going to be the opposite. In an exothermic reaction, energy is released. So if my reactants have 10, my products have 5, and I subtract them, I do 5 minus 10, I get a negative 5 kilojoules. The sign is very important here. In an exothermic reaction, the delta H is always going to have a negative sign. Now, reference table I is what we're going to use to determine the heat of reaction at 101.3 kilopascals and 298 Kelvin. 101.3 kilopascals is also 1 atmosphere, which is standard pressure. 298 Kelvin is 25 degrees Celsius, which is basically like room temperature. It's not standard temperature, it's room temperature. So you get a list of reactions here, and it shows if the reaction is endo or exothermic. So here's what reference table I looks like. It's just this long list of different reactions. It gives you the formulas, it gives you the delta H values. And then at the bottom, on the bottom it tells you that the minus sign indicates an exothermic reaction. So you never have to even remember that, it tells you that. I want to show you these first 3. The first reaction, these are all called combustion. You have a hydrocarbon reacting with oxygen to form carbon dioxide and water. So every single one of these is called a combustion reaction. When you talk about combustion, you think about explosions or burning. So that's obvious that they're going to give off energy, but you can see how the amount of energy changes as you change the reaction. And it has to do with the size of the hydrocarbon that you're reacting. So that first hydrocarbon that's there, CH4, that's methane, which you should know that methane is CH4. That's natural gas. So yes, natural gas burns and gives off energy. We use it as a common fuel. The second one there, C3H8, that is propane. So propane is what you use in a gas grill. That gives off more energy than methane does. This last one, C8H18, is octane. And octane is what you'd find in gasoline. So that gives off even more energy. Another reaction that you might be familiar with here is this one. That's cellular respiration. right? Glucose plus oxygen produces CO2 and H2O, and it gives off energy. We talk about it in terms of ATP in biology, but we're looking at it in kilojoules in chemistry. So you have a variety here. These two here, I want you to make note of. They both are producing water, but this is producing water vapor and this is producing liquid water. So more energy is given off when you produce liquid water because you have to take the gas and convert it to a liquid, which releases energy. These reactions at the bottom here that have the water listed above the arrow, these are all the heats of solution. You're dissolving the reactant into water. So you can see that some things, when they dissolve, they absorb energy, and some things release energy. The very last equation on here should be somewhat familiar to you. Hydrogen plus hydroxide makes water. That's neutralization. So neutralization is actually an exothermic process. So I'm going to show you some examples of questions you have to know how to answer here, but that's all there really is to this, is reading a reaction and telling whether it's endo or exothermic. So for the first one, we're given a reaction, give the delta H, tell if it's endo or exo. Well, the delta H is negative 890.4, so that would be exothermic. The second one, two CH3OH, that's a combustion of methanol. So that is negative 1452, which would also be exothermic. And then we look at this third one, N2 plus O2 makes 2NO. Be careful because these both are nitrogen and oxygen, so you have to make sure you read the right reaction. This has a positive 182.6 kilojoules, which makes it endo. Now look at these follow-up questions. How much heat is needed to produce 2 moles of NO? Anytime we're talking about moles, we look at the coefficient in the balanced equation, which is 2. So since we're talking about the number that's in the equation, it's just 182.6 kilojoules. Now the second part here, how much heat is needed to produce 1 mole of NO? Well, there's 2 moles produced, if 182.6 kilojoules are absorbed when 2 moles of NO are produced, how many kilojoules are absorbed when 1 mole is produced? So since we're cutting it in half, it would just be cut in half. So it's just proportionate. All you have to do is look and see if they manipulated the coefficient. It's just basic stoichiometry. So here's this question, how much heat is needed to produce 2 moles of HI? So I'm going to find the reaction that produces HI, look and see its coefficient. Oh, it matches. So I just have to read the graph. But if I cut the number of moles of HI in half, I would have to cut the number of kilojoules in half as well. So that would be 26.5 kilojoules. Heat of formation, you know what, this isn't even really tested. I'll explain what it is real quick. Heat of formation is the amount of energy needed to make 1 mole of a compound. So the heat of formation of NO, when you look at this, there's 2 moles produced, so that's the amount of energy. Heat of formation would have to be, you'd cut it in half because it's how much is needed to produce 1 mole, but again, that's never going to be asked in the Regents, so we'll just leave that alone. And the last part here is, if you're given a question that says like which substance is more stable, the more negative the delta H value, the more stable the compound is. So looking at the ammonia of negative 91.8 and the water vapor, which is negative 483.6, this would be more stable because it has a more exothermic process. More energy is given off during the process, so it ends up being more stable. So really that's all there is to doing table I. There's a worksheet in OneNote for you to do some practice questions. Let me know if you have any questions.